Muriel Richard. I'm presenting here the work of a whole team for a year, presenting the results, summarizing the results of the GSTP activity that we did over the last almost 12 months. The topic here today is on active debris removal. I think you're all aware that removing large debris is becoming a priority, at least in the next 10 to 20 years. There is an ESA program for this called the Clean Space Program. And that Clean Space Program has been working with us, and basically we've been working with them on this question of active debris removal. The context is the following. First of all, active debris removal is an expensive business, at least in the development phase. What we're targeting there is very large debris that are third stages, that are very old, rocket bodies coming from many different sources and countries. And the orbit studies that ESA has been performing is targeted toward 8-ton type debris, very large, something that resembles very much CubeSat. So removing those types of debris will be a quite a cost-intensive project, and it will involve risky maneuvers and operations, which will call most of the times for new technologies. So the question was, what can we do with CubeSats and CubeSats in-orbit demonstrations in order to remove some of the risk for these very large missions? And this is the question that ESA asked in their statement of work. Show us what validation demonstration can be done with CubeSats, perform technology trade-offs, produce a make or buy list of active debris removal technologies recommended for demonstration, and show a development plan for each of these technologies. So our response to this, or maybe I should state that this is part of the Clean Space program that you see here. If this works, okay, maybe not. So this is part of the Clean Space program, and this CubeSat technology IoT is right here. So the way we responded to this question was by forming a consortium and identifying 4 major tasks. The first one was the mission identification and requirements definition, so mission scenarios that could help the community, the ADR community, for demonstrations. And we did this with partners, the University of Bern, as well as the ETH CETS in Zurich, the Federal University in Switzerland. Then that was the first task. Then we went to a second task, which was the evaluation of different technologies that could be demonstrated and would be interested in demonstrating. So here we had 4 partners: the CSEM on the vision-based rendezvous sensors, the Applied Science University from Yverdon, which is very close to here, looked at radar-based rendezvous sensors. Also had capture systems evaluated from with the help of ETH CETS, and micropropulsion systems with a lab from EPFL. So all of these evaluations helped us define the technologies that would need to be demonstrated with the CubeSats. And in parallel to this, we had a third task, which was the actual CubeSat conceptual designs. In the end of this technical activity, 2 industrial partners joined us, Mikos and WAG, and both of them established roadmaps for those technologies to be developed. There's ADR specific technologies to be developed. So the first question in the first task was, you want to go remove large debris from space. What can you do with CubeSats? Is it really scalable? So how representative and scalable is a CubeSat mission to the removal of very large debris? And the way we tackle this, we looked at the different functions that the ADR system needs to perform, and function by function, we came up with an evaluation that took quite a long time and many iterations because this is a tricky question. But here you can see in this table the debris function, the main functions, and our evaluation of the scalability and of the need. I won't go into details, but basically what came out is that the debris detection, the debris motion and reconstruction of the geometry and the motion of the debris were good candidates. The whole testing of the dynamic of a tethered system, if you have a net to attach and capture the debris, the whole dynamic of this tethered system was also a good potential option for demonstration. And all that was related to the net systems deployment and closing were also very good options. So we came up with about 10 different mission scenarios that we evaluated and for their interest, of course with ESA. And at the end we selected 2 missions that we called CADRE for CubeSat ADR experiment. The first one is to test some of the rendezvous sensors, and the second one would be to test net capture systems. So I'll go in the details of the first one. The second one is very similar to the first one. And the test of the CADRE 1, which is the test of the rendezvous sensors, from a demonstration perspective of those rendezvous sensors, we came up with a mission analysis that looks as such. So you start, and I will try to use the pointer here. This is a graph showing R bar versus B bar, so it's centered toward the debris. And here in this configuration of the system, we start with a linked design between the CubeSat, 2 CubeSats, a chaser, and a debris. At some point when it's whole detumbled, we're done with the commissioning phase. We separate both objects and move the target, move the chaser, to this station keeping point that's about 20 meters away. At that point, we start having a series of motion reconstructions and observations with different type of spins of the target. We do this about 15 times, so 15 fly rounds. In that time, we actually gather a lot of information from the science, from the rendezvous sensors, sand it all down to the ground where it's being reconstructed, so all the algorithms can be done on the ground, potentially also on board. Once we were done with all these observations, then we move to a second phase, which is a phase where we move away from the target to about 7 kilometers, and we push ourselves into drift orbit, and those drift orbits allow us to test the handover between the absolute navigation to the relative navigation, again with different sensors. So this mission design is quite complex, and the first question that we asked ourselves with the CSEM was which rendezvous sensors should we select? So here we have a review of all the 1D, 2D, and 3D rendezvous sensors and evaluated those against all these different criteria, which I won't go into details, but those are very specific to the GNC capabilities. And we ended up selecting a set of 3 to 4 different sensors. Some of them one of them is the flash LiDAR, another one is an infrared camera, another one is a regular vision camera, and the other one is a radar. I'll show this to you in how that fits into the configuration in the next few slides. Now the next question that came up was, can we really do all of this with the CubeSat? So such a complex mission design, flying those new technologies, especially the flash LiDAR, can we actually fit all of this into a CubeSat? And so to do this, we ended up doing several systems analysis, which you see here I'll describe in a second. The first analysis was on the matching of the ballistic coefficient. One of the problems is if you want to go remove, for instance, NBSat, you're at 700 kilometer altitude, there isn't much drag out there. For a CubeSat mission, you want to make sure that you will re-enter within the 25-year rule, so you're below 600, around maybe 500 kilometer or so altitude, so you do have drag. So for this, you need to compensate for those drag effects. And this analysis showed at least in the first order, that we could, with some propulsion, we could actually match those ballistic coefficients and replicate what would be seen at higher altitudes. So we were pretty happy with this. Then we looked into the different and the requirements for attitude control between the chaser and the target, selected available COT sensors and actuators that you find on the market for CubeSat and performed the analysis. That showed that on the order of magnitude, we could get to about a degree pointing accuracy at about a tenth of a degree on the stability, which from the point of view of the rendezvous sensors was plenty acceptable. So we were also pretty happy about this. Then we looked at a big question, which is how do you manage the energy inside the system? And we ended up having to design a CubeSat with 4 deployable solar panels, which would be a custom design. With that, we performed but simulations of the need of each of the subsystems as you go along and perform these maneuvers around in your orbit. So here is a graph showing when the rendezvous sensors would be used, the ADCS would be turned on, and so on as a function of time. And we looked at how the batteries will be depleted. So we looked at the depth of discharge of these batteries, and we ended up with a design that also was satisfactory. The last, one of the last subsystems, but this is a very crucial subsystem because now you really want to bring agility to your CubeSat. So propulsion is of definite criticality. The need for this Cadre 1 was defined in terms of delta V and also thrust level. We had about 40 meters per second that we needed for that mission. Very large number of cycles, valve cycles, and this the PWM control that we used. And again, we did a selection, looked at different technologies that are available out there, and ended up selecting the nanospace design, which allows throttleable and continuous thrust, and also allows a design which is quite modular and fits nicely into a CubeSat. So we're pretty happy to see that there would be some modifications to this system, because right now the system only has 1 thruster, but the evolution of that system to a 12 thruster module seemed to be achievable. Another question was on the processing capabilities that you need on board for the rendezvous sensors. And again, the engineering schools here have expertise in that domain, and they helped us as the partners, and they defined and found FPGAs and combinations of FPGAs and DSPs that could fit our requirements. So here again, all of this is commercial off the shelf. And so we were pretty happy that it worked out. Now, the last question was, now very well, you have 4 rendezvous sensors, so a flash LiDAR, infrared camera, a regular camera, visible camera, and a radar. How does that really fit in terms of the volume? It fits in terms of the power, but how did that fit in terms of the volume? So our configuration engineers scratched their heads for quite some time. And considering all the constraints of being able to have GPS pretty much all the time, have telecommunication in the critical phases, have the solar panels looking at the sun at the same time, having the rendezvous sensors looking at the target pretty much in real time and continuously. We found a solution. There may be other solutions that exist, but we found a solution that all fit into an 8-unit CubeSat. That 8-unit CubeSat, you will be able to see it. We have a model here during the break. I suppose we have a model here sitting on the table. This is a CAD drawing of it. It has the sensors and some details of how things are fitting inside. So basically, it would be a launch of a 12-unit system, an 8-unit chaser, and a 4-unit target. And those would be separated once you're done with the commissioning. So all of this worked out, and we were pretty happy to present this to ESA. The Cadre 2 mission, Cadre 3 mission, sorry, which tests the capture and dynamic of the net, is pretty similar. I won't go in the details of it, but it offers quite a bit actually of capability. So in conclusion, we looked at the scalability and feasibility of in-orbit demonstrations of the ADR technologies with CubeSat. We ended up proposing 2 mission scenarios to test the rendezvous sensors and the net technology. It turned out that in both of these scenarios we could fit the chaser into a 8-unit configuration with enough margin on the power, mass and volume budget. The target CubeSat would fit into a 4-unit, and that had plenty of space. So the ADR technologies that we identified for the rendezvous, both on the vision and radar-based systems and the net capture systems, some of these technologies can be found on the shelf, so that could be actually tested quite fast. Some others actually do need quite a bit of development, and this is why our industrial partners will be continuing those developments. Now, what we also stated to ESA is that this analysis had the goal of showing a capability, things that you can do with CubeSats, and it is, will be possible to change some of these mission scenarios and adapt them for the need of the large industrial consortium that the Clean Space program is involving, to make them match their particular needs. So this is what we ended up doing over this last year. Thank you. I will take.
Thank you very much. I think we have time for one quick question. So I had one question, and this was with your attitude, determination. You had mentioned you needed to have knowledge to about a degree, but I saw you didn't have any star trackers to give you knowledge on the night side. So I didn't, to get a degree, you need something about an arc second per second or 2 arc seconds per second on your rate gyro to hold that.
Right.
So I didn't. Getting that type of performance?
Yeah, yes. Well, that was identified as the star trackers. We tried first to fit them into the CubeSat. Unfortunately, at the time where we were doing this analysis, we had a problem with very large baffles, because the star trackers will need baffles. Now, we've seen recently that there are new designs where the baffles are a lot shorter, so we would need to reevaluate this. What we ended up doing is making several iterations on the ATCS. And without the star trackers, we ended up having a attitude control to about 2 degrees per second, 2 degrees pointing accuracy, and about 2.1 also on the stability, which was relaxed compared to the requirements. But we also saw, going along, that was not a problem for the rendezvous sensors. So there was some margin in our ATCS that we felt comfortable flying without star trackers. Now that we have seen recent developments in the next phase, I believe that we will definitely try to integrate the star trackers to, again, improve on the ATCS.
Excellent. Okay, thank you very much.
Thank you.